Hi. Hello everyone. Welcome to information sharing session on failure analysis. In previous session, we discussed about surface defects that we come across in extrusion process. Today, we will discuss about dimensional defects and internal defects encountered in extrusion process. Dimensional inconsistency in extrusion. Imperfect shapes and sizes. Dimensional inconsistency refers to deviations in the actual dimensions of an extruded product from the desired specifications. This defect manifests as variations in length, diameter, thickness, or other critical dimensions across different sections of the extrudate, or between different products produced in the same batch. Causes of dimensional inconsistency. Several factors contribute to dimensional inconsistencies in extruded products. Uneven material flow. Inconsistent flow of material through the die can lead to variations in cross-sectional area and, consequently, inconsistent dimensions. This can be caused by factors like improper die design, abrupt transitions, sharp corners, or inadequate venting within the die can disrupt smooth flow. Variable material properties. Differences in viscosity or temperature across the material can affect flow. Fluctuations in process parameters. Inconsistent pressure, temperature, or flow rate can contribute to uneven flow. Die wear and contamination. Wear and tear on the die land can create irregularities that affect material flow and lead to dimensional inconsistencies. Foreign particles on the die surface can also act as flow disruptors. Temperature variations. Uneven temperature distribution within the die or the material can lead to differential shrinkage during cooling, resulting in dimensional changes. Improper material preparation. Insufficient drying or preheating of the material can affect its flow properties and contribute to dimensional variations. Handling and cooling. Improper handling of the extrudate after exiting the die or uneven cooling can induce distortions and dimensional changes. Consequences of dimensional inconsistency. Dimensional inconsistencies can have significant consequences for the extruded product. Functional issues. Products with inconsistent dimensions may not fit properly in intended applications, leading to performance issues or even failures. Assembly challenges. Incompatibility with other parts due to dimensional deviations can create assembly difficulties and delays. Material waste. Products with significant dimensional inconsistencies may be deemed unusable and discarded, leading to material waste and increased costs. Customer dissatisfaction. Inconsistent products can lead to customer dissatisfaction and reputational damage for the manufacturer. Minimizing dimensional inconsistency. Several strategies can be implemented to minimize dimensional inconsistencies in extrusion. Optimizing die design. Employing advanced die design techniques with smooth transitions, rounded corners, and appropriate venting channels can promote uniform material flow and consistent dimensions. Maintaining die quality. Regularly cleaning and inspecting the die land to prevent wear and ensure a smooth surface for optimal flow. Controlling process parameters. Implementing precise control systems to maintain consistent temperature, pressure, and flow rate throughout the extrusion process. Using high-quality materials. Selecting materials with consistent properties and minimal variations in viscosity or temperature sensitivity can improve dimensional control. Optimizing material preparation. Ensuring proper drying and preheating of the material before extrusion can enhance its flow properties and minimize shrinkage during cooling. Implementing real-time monitoring. Utilizing sensors and monitoring systems to track key parameters like temperature, pressure, and flow rate can allow for real-time adjustments and prevent dimensional variations. Employing proper handling and cooling procedures. Implementing proper handling techniques and ensuring uniform cooling can minimize post-extrusion distortions and maintain dimensional accuracy. By understanding the causes and consequences of dimensional inconsistencies and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with consistent and reliable dimensions, leading to improved functionality, reduced waste, and enhanced customer satisfaction. Remember, precision and control are key to achieving optimal dimensional accuracy in extrusion processes. Warpage in extrusion. Shapes gone awry. Warpage in extrusion refers to the undesirable bending or distortion of the extruded product's cross-section from its intended flat, straight, or regular shape. This defect can significantly impact the product's functionality, aesthetics, and even its ability to be used for its intended purpose. Causes of warpage. Warpage can arise from various factors during the extrusion process. Uneven cooling. Uneven heat distribution within the extrudate during cooling can lead to differential shrinkage, causing the material to warp in the direction of the faster cooling zone. This can be due to inadequate die design. Poor die design can create uneven cooling channels or hot spots within the die. Improper cooling methods. Inconsistent airflow, uneven contact with cooling surfaces, or rapid cooling can lead to uneven shrinkage. Internal stresses. Residual stresses trapped within the material during extrusion can be released during cooling, causing the extrudate to warp. This can be caused by high extrusion pressure. Excessive pressure can lead to internal stress buildup. Improper material selection. Materials with high thermal expansion coefficients are more prone to stress-induced warpage. Anisotropic material properties. Some materials exhibit different properties in different directions, which can lead to uneven shrinkage and warpage during cooling. Die wear and contamination. Worn or contaminated die land can cause uneven flow and stress concentrations, leading to warpage. Improper handling. Rough handling of the extrudate after exiting the die can induce additional stress and contribute to warpage. Consequences of warpage. Warpage can have significant consequences depending on the severity and application of the extruded product. Functional issues. Warped products may not fit properly in their intended applications, leading to performance failures or assembly difficulties. Aesthetic appeal. For products where appearance matters, warpage can significantly detract from their visual appeal, making them commercially undesirable. Material waste. Warped products may be deemed unusable and discarded, leading to material waste and increased production costs. Safety concerns. In extreme cases, severe warpage can compromise the product's structural integrity, raising safety concerns in certain applications. Preventing and minimizing warpage. Several strategies can be employed to minimize the occurrence of warpage. Optimizing die design. Employing advanced die design techniques with symmetrical channels, uniform cooling passages, and stress-relieving features can significantly reduce warpage. Controlling process parameters. Maintaining consistent temperature, pressure, and flow rate throughout the extrusion and cooling process can minimize internal stresses and uneven shrinkage. Selecting appropriate materials. Choosing materials with low thermal expansion coefficients and isotropic properties can inherently reduce the risk of warpage. Implementing proper cooling methods. Utilizing controlled cooling techniques with uniform airflow and contact pressure ensures even heat dissipation and minimizes differential shrinkage. Minimizing internal stresses. Optimizing pressure profiles and implementing stress-relieving techniques during extrusion can help manage internal stresses and prevent warpage. Maintaining die quality. Regularly inspecting and cleaning the die land to prevent wear and ensure smooth flow for optimal stress distribution. Implementing proper handling procedures. Careful handling of the extrudate after exiting the die and during cooling can minimize additional stress and warpage. By understanding the causes and consequences of warpage and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with consistent shapes and dimensions, leading to improved functionality, aesthetics, and overall product value. Remember, small adjustments in process parameters and die design can often make a significant difference in achieving optimal shape stability in your extruded products. Twisting in extrusion. When shapes go askew. Twisting in extrusion refers to the undesirable rotation or torsion of the extruded product along its longitudinal axis. This defect manifests as a deviation from a straight profile, resulting in a product that is bent or curved in a spiral fashion. While seemingly minor in some cases, twisting can significantly impact the functionality, aesthetics, and usability of the extrudate. Causes of twisting. Several factors can contribute to twisting during the extrusion process. Uneven material flow. Inconsistent flow of material through the die can create unbalanced forces within the extrudate, leading to torsional stress and twisting. This can be caused by improper die design, abrupt transitions, sharp corners, or asymmetrical channels within the die can disrupt flow and create unbalanced forces. Material variations. Differences in viscosity or temperature across the material can affect its flow behavior and contribute to uneven forces. Fluctuations in process parameters. Inconsistent pressure, temperature, or flow rate can lead to uneven material distribution and twisting. Die wear and contamination. Worn or contaminated die land can create irregularities that disrupt flow and induce torsional stress, leading to twisting. Material properties. Certain materials, particularly those with anisotropic properties, different properties in different directions, are more prone to twisting due to uneven shrinkage during cooling. Cooling inconsistencies. Uneven cooling can lead to differential shrinkage across the extrudate, inducing twisting as different sections contract at different rates. External forces. Improper handling or external forces applied to the extrudate after exiting the die can induce twisting. Consequences of twisting. The severity of twisting can have significant consequences for the extruded product. Functional issues. Twisted products may not fit properly in their intended applications, leading to performance failures or assembly difficulties. Aesthetics. Twisting can significantly detract from the product's appearance, making it commercially undesirable and unsuitable for certain applications. Material waste. Products with severe twisting may be deemed unusable and discarded, leading to material waste and increased costs. Safety concerns. In critical applications, twisting can compromise the product's structural integrity, raising safety concerns. Preventing and minimizing twisting. Several strategies can be employed to minimize the occurrence of twisting. Optimizing die design. Employing advanced die design techniques with symmetrical channels, smooth transitions, and balanced flow patterns can significantly reduce the risk of twisting. Maintaining consistent process parameters. Implementing precise control systems to maintain consistent temperature, pressure, and flow rate throughout the extrusion process can minimize unbalanced forces and twisting. Selecting appropriate materials. Choosing materials with isotropic properties and minimal thermal expansion coefficient variations can inherently reduce the risk of twisting due to uneven shrinkage. Controlling cooling conditions. Utilizing effective cooling methods with uniform airflow and contact pressure can ensure even heat dissipation and prevent differential shrinkage-induced twisting. Minimizing internal stresses. Optimizing pressure profiles and implementing stress-relieving techniques during extrusion can help manage internal stresses and prevent torsional forces. Maintaining die quality. Regularly inspecting and cleaning the die land to prevent wear and ensure smooth flow for optimal force distribution. Implementing proper handling procedures. Careful handling of the extrudate after exiting the die and during cooling can minimize external forces that could induce twisting. By understanding the causes and consequences of twisting and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with straight and stable profiles, leading to improved functionality, aesthetics, and overall product value. Remember, attention to detail in die design, process control, and material selection can go a long way in achieving optimal shape stability and preventing unwanted twisting in your extruded products. Swelling in extrusion. When shapes expand beyond limits. Swelling in extrusion refers to the undesirable enlargement of the cross-section of the extruded product beyond its intended dimensions. This defect manifests as a product that is thicker or wider than it should be, compromising its functionality, aesthetics, and even its ability to fit into intended applications. While seemingly minor in some cases, swelling can have significant consequences for the manufacturing process and the final product. Causes of swelling. Several factors can contribute to swelling during the extrusion process. High extrusion pressure. Excessive pressure applied during extrusion can force the material against the die land with greater force, causing it to expand beyond the die cavity. Improper die design. Die channels that are too narrow or have sharp corners can restrict material flow, leading to increased pressure and subsequent swelling. Material properties. Certain materials, particularly those with high thermal expansion coefficients or low melt viscosity, are more prone to swelling due to their tendency to expand significantly when heated. Improper temperature control. Excessively high temperatures during extrusion can cause the material to expand beyond its intended dimensions. Gas entrapment. Air trapped within the material during extrusion can expand when heated, causing the extrudate to swell. This can be due to moisture content. High moisture content in the material can vaporize during extrusion, creating voids and contributing to swelling. Incomplete degassing. Insufficient removal of trapped air from the material before extrusion can lead to gas entrapment and swelling. Die wear and contamination. Worn or contaminated die land can create areas of high friction or flow restrictions, contributing to uneven pressure distribution and localized swelling. Consequences of swelling. The severity of swelling can have significant consequences for the extruded product. Dimensional inconsistencies. Swelling can lead to significant variations in the product's dimensions, making it incompatible with intended applications or assembly processes. Functional issues. Products with excessive swelling may not function properly or fit into their intended spaces, leading to performance failures or assembly difficulties. Material waste. Products with severe swelling may be deemed unusable and discarded, leading to material waste and increased production costs. Safety concerns. In critical applications, swelling can compromise the product's structural integrity, raising safety concerns. Preventing and minimizing swelling. Several strategies can be employed to minimize the occurrence of swelling. Optimizing process parameters. Fine-tuning pressure, temperature, and flow rate can significantly impact swelling by minimizing applied force, controlling heat exposure, and ensuring smooth material flow. Employing proper die design. Utilizing advanced die design techniques with appropriate channel dimensions, smooth transitions, and adequate venting can prevent flow restrictions and pressure buildup. Selecting appropriate materials. Choosing materials with lower thermal expansion coefficients and higher melt viscosity can inherently resist swelling during extrusion. Maintaining proper temperature control. Implementing precise temperature control systems throughout the extrusion process ensures optimal material flow and minimizes excessive heat-induced expansion. Implementing effective degassing techniques. Employing pre-drying or vacuum degassing techniques can remove trapped air from the material before extrusion, preventing gas entrapment and swelling. Maintaining die quality. Regularly cleaning and inspecting the die land to prevent wear and ensure smooth flow for optimal pressure distribution and minimize localized swelling. Monitoring and controlling process parameters. Implementing real-time monitoring systems to track pressure, temperature, and other parameters can allow for prompt adjustments and prevent swelling before it occurs. By understanding the causes and consequences of swelling and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with accurate dimensions, optimal functionality, and minimal waste. Remember, careful control of process parameters, proper die design, and material selection can go a long way in achieving dimensional stability and preventing unwanted swelling in your extruded products. Voids in extrusion. Hidden enemies within. Voids, also known as internal cavities or air pockets, are a common and often insidious defect in extruded products. Unlike surface defects like scratches or tears, voids remain hidden within the material, making them difficult to detect and potentially compromising the product's functionality and integrity. Formation of voids. Voids can form within the extrudate due to various factors during the extrusion process. Gas entrapment. Air trapped within the material during processing can expand and create voids within the extrudate. This can occur due to moisture content. Excessive moisture in the material can vaporize during extrusion, leaving behind voids. Incomplete degassing. If trapped air isn't adequately removed before extrusion, it can expand and cause void formation. Material properties. Materials with naturally high gas content are more prone to void formation. Shrinkage differences. Uneven shrinkage of the material during cooling can create internal voids, particularly in thick or complex sections of the extrudate. Flow irregularities. Inconsistent flow of material through the die can lead to localized areas of low pressure, creating voids as the material solidifies. This can be caused by improper die design. Sharp corners or abrupt transitions within the die can disrupt flow and create areas of low pressure. Fluctuations in process parameters. Inconsistent pressure, temperature, or flow rate can lead to uneven flow and void formation. Die wear and contamination. Worn or contaminated die land can create irregularities that disrupt flow and trap air, contributing to void formation. Consequences of voids. The severity and location of voids can have significant consequences for the extruded product. Reduced mechanical properties. Voids weaken the material, compromising its strength, stiffness, and fatigue resistance. This can lead to failures in critical applications. Leakage and fluid infiltration. Voids can allow liquids or gases to pass through the material, compromising its functionality and potentially leading to safety concerns. Reduced aesthetics. In some cases, voids can create visible surface imperfections, detracting from the product's visual appeal. Increased production costs. Identifying, correcting, and discarding products with voids can lead to production downtime, material waste, and increased costs. Preventing and minimizing voids. Several strategies can be employed to minimize the occurrence of voids during extrusion. Controlling moisture content. Pre-drying the material to remove excess moisture can significantly reduce gas entrapment and void formation. Implementing effective degassing techniques. Utilizing vacuum degassing or other techniques can remove trapped air before extrusion, minimizing internal voids. Optimizing process parameters. Fine-tuning pressure, temperature, and flow rate throughout the process ensures proper material flow and minimizes air entrapment. Employing proper die design. Utilizing advanced die design techniques with smooth transitions, adequate venting channels, and optimized flow patterns prevents flow irregularities and reduces void formation. Maintaining die quality. Regularly cleaning and inspecting the die land to prevent wear and ensure smooth material flow minimizes air trapping and void formation. Controlling cooling conditions. Implementing controlled cooling with consistent temperature and pressure distribution throughout the extrudate prevents differential shrinkage and minimizes internal void formation. Monitoring and controlling process parameters. Implementing real-time monitoring systems allows for prompt adjustments to process parameters before they contribute to void formation. By understanding the formation, consequences, and mitigation strategies for voids, manufacturers can ensure high-quality extruded products with optimal mechanical properties, functional performance, and aesthetic appeal. Remember, vigilance and proactive measures in controlling moisture, gas entrapment, and flow irregularities can significantly reduce the risk of these hidden enemies within your extruded products. Inclusions. Unwelcome guests in your extruded products. Inclusions, also known as foreign particles or contaminants, are unwanted materials embedded within the extruded product. These unwelcome guests can be anything from tiny metallic fragments to bits of dirt or even trapped air bubbles. While seemingly insignificant at times, inclusions can have a significant impact on the functionality, aesthetics, and even safety of the final product. Sources of inclusions. Raw materials. Contaminated raw materials, such as oxides, scales, or other impurities present in the initial feedstock, can end up embedded within the extrudate. Processing equipment. Wear and tear on the extrusion equipment, such as chips from the die land or dust from internal components, can become incorporated into the material during processing. External environment. Dust, dirt, or other airborne contaminants can enter the material stream during handling or processing, leading to inclusions. Lubrication. Improperly selected or applied lubricants can break down or leave residue within the extrudate, creating inclusions. Consequences of inclusions. The severity of the consequences depends on the size, type, and location of the inclusions. Reduced mechanical properties. Inclusions can act as stress concentrators, weakening the material and compromising its strength, stiffness, and fatigue resistance. This can lead to premature failures, particularly in critical applications. Surface imperfections. Visible inclusions can detract from the product's aesthetic appeal, impacting its marketability and consumer satisfaction. Functional issues. Certain inclusions, like air bubbles, can compromise the product's functionality by creating voids or channels for fluid leakage. Safety concerns. In extreme cases, inclusions can lead to catastrophic failures if they compromise the product's structural integrity or introduce potential ignition points. Preventing and minimizing inclusions. Several strategies can be employed to minimize the risk of inclusions in extruded products. Raw material selection and processing. Implement stringent quality control measures on the raw materials to ensure their purity and cleanliness. Additionally, consider pre-cleaning or filtering the material before extrusion. Maintaining equipment. Regularly inspect and maintain extrusion equipment to prevent wear and tear that could contribute to inclusions. Promptly replace worn-out components and implement preventive maintenance programs. Controlling the processing environment. Minimize dust and other airborne contaminants in the processing area. Implement air filtration systems and maintain clean handling procedures. Optimizing lubrication. Choose appropriate lubricants and ensure proper application techniques to minimize residue or breakdown within the extrudate. Implementing filtration systems. Utilizing melt filters or other filtration techniques can capture and remove inclusions before they become embedded in the final product. Visual inspection and testing. Implement routine visual inspection and non-destructive testing methods to identify potential inclusions early in the production process. By understanding the sources and consequences of inclusions, manufacturers can implement effective preventive measures to ensure high-quality extruded products free from these unwelcome guests. Remember, vigilance in material selection, equipment maintenance, and process control can significantly reduce the risk of inclusions and improve the overall reliability and performance of your extruded products. Degradation in extrusion. When polymers lose their shine. Degradation refers to the undesirable breakdown of the polymer chains within the material during the extrusion process. This phenomenon weakens the material's properties, leading to compromised functionality, aesthetics, and even safety concerns in the final product. Causes of degradation. Several factors can contribute to polymer degradation during extrusion. Thermal stress. High temperatures encountered during extrusion can break down the polymer chains through thermal scission, a process where chemical bonds within the polymer backbone are broken due to excessive heat. Shear stress. The frictional forces experienced by the material during flow through the die can mechanically rupture the polymer chains. Oxidative degradation. Exposure to oxygen, especially in the presence of high temperatures, can lead to the formation of free radicals, which further degrade the polymer chains. Hydrolytic degradation. Moisture present in the material or the processing environment can react with the polymer chains and break them down. Chemical reactions. Certain additives or contaminants within the material or the processing environment can react with the polymer chains, causing degradation. Radiation exposure. Exposure to ionizing radiation, such as ultraviolet light, can break down the polymer chains through similar mechanisms as thermal degradation. Consequences of degradation. The severity of the consequences depends on the degree of degradation. Reduced mechanical properties. Degraded polymers exhibit decreased strength, stiffness, and fatigue resistance, leading to potential failures in applications requiring high performance. Increased viscosity. Degradation can alter the flow properties of the material, making it more difficult to process and potentially impacting product dimensions or surface finish. Color changes. Breakdown of the polymer chains can affect the material's color, leading to discoloration or unevenness in appearance, impacting the product's aesthetics. Gas generation. Certain degradation reactions can release volatile gases, potentially creating voids or bubbles within the extrudate and compromising its integrity. Environmental concerns. Some degradation products can be harmful to the environment or human health, requiring careful handling and disposal of degraded materials. Preventing and minimizing degradation. Several strategies can be employed to minimize polymer degradation during extrusion. Optimizing process parameters. Controlling temperature, pressure, and residence time within the extruder can significantly reduce thermal and shear stress, minimizing chain scission. Inert atmosphere processing. Utilizing an inert gas environment during extrusion can prevent oxidative degradation and minimize exposure to oxygen. Material selection and purification. Choosing polymers with inherent stability to degradation and implementing effective drying techniques to remove moisture from the material can significantly reduce degradation risks. Additives and stabilizers. Utilizing antioxidants, thermal stabilizers, and other additives can help scavenge free radicals and inhibit degradation reactions. Equipment maintenance and optimization. Maintaining the extruder in good condition and optimizing die design can reduce frictional forces and minimize shear stress on the material. Monitoring and control. Implementing real-time monitoring systems for temperature, pressure, and other parameters allows for proactive adjustments to prevent excessive degradation. By understanding the causes and consequences of degradation and implementing effective preventive measures, manufacturers can ensure high-quality extruded products with optimal properties, performance, and aesthetic appeal. Remember, careful control of process parameters, a focus on material stability, and the use of appropriate additives can significantly prolong the life and maintain the integrity of your extruded polymers. Cracks in extruded products are more than just cosmetic blemishes, they represent a deeper vulnerability in the material's integrity. These surface fissures can compromise the product's functionality, performance, and even safety, impacting its marketability and lifespan. Understanding the different types of cracks and their root causes is crucial for manufacturers to prevent them and ensure high-quality extrudates. Types of cracks in extrusion. Degradation-induced cracks. These cracks arise from the breakdown of the polymer chains within the material due to factors like thermal stress, oxidative degradation, or hydrolysis. This weakening compromises the material's cohesion and makes it more susceptible to cracking under stress. Surging-induced cracks. Sudden increases in pressure or flow rate within the die channel can cause localized stress concentrations exceeding the material's tensile strength, leading to surface cracks. These surges can be triggered by fluctuations in process parameters, die design limitations, or even equipment malfunctions. Stress cracking. Mechanical stresses experienced during processing, handling, or even during service life can exacerbate existing weaknesses and initiate crack formation. This can be caused by factors like bending, twisting, or impact forces. Environmental stress cracking. Exposure to certain chemicals or environmental conditions like UV light or ozone can induce internal stresses and accelerate crack formation in susceptible materials. This type of cracking can occur even after the extrusion process is complete. Consequences of cracks. The severity of the consequences depends on the type, depth, and location of the cracks. Reduced structural integrity. Cracks compromise the material's strength and stiffness, making it susceptible to failure under stress and reducing its load-bearing capacity. This can be critical in safety-related applications. Leakage and fluid ingress. Cracks can provide pathways for liquids or gases to enter the material, compromising its functionality and potentially posing safety hazards in applications involving fluids or pressurized environments. Aesthetics and marketability. Visible cracks detract from the product's visual appeal, making it commercially undesirable and potentially impacting customer satisfaction. Increased production costs. Identifying, repairing, and discarding cracked products leads to production downtime, material waste, and increased costs. Preventing and minimizing cracks. Several strategies can be employed to prevent crack formation and ensure crack-free extrudates. Process control. Maintaining consistent temperature, pressure, and flow rate throughout the extrusion process minimizes stress and degradation. This includes proper equipment maintenance, die design optimization, and real-time monitoring and control systems. Material selection and processing. Choosing materials with inherent crack resistance and implementing premixing or degassing techniques can enhance crack resistance and prevent air entrapment. Stress management. Employing proper handling techniques and avoiding excessive bending or twisting forces during processing and service life can minimize stress-induced cracking. Environmental protection. Protecting the extrudate from exposure to UV light, ozone, or other aggressive chemicals can prevent environmental stress cracking. Cracking detection and mitigation. Implementing visual inspection methods and non-destructive testing techniques can help detect cracks early and prevent them from propagating further. By understanding the different types of cracks, their root causes, and the potential consequences, manufacturers can implement effective preventive measures and ensure the production of high-quality, crack-free extruded products with optimal performance, aesthetics, and long-term durability. Remember, a proactive approach to process control, material selection, and stress management is key to minimizing these surface scars and achieving consistent quality in your extruded products. In next session, we will go through flow-related and other extrusion process defects. Thank you.